Welcome to this presentation on the strategy design pattern. Let's start by looking at a simple but common scenario. Imagine you're building a video game with a variety of characters: knights, archers, and wizards. Each has a unique way of attacking. Knights strike with swords, archers shoot arrows, and wizards cast spells. At first glance, this seems like a textbook case for inheritance. You might set up a base class called character with subclasses like knight, archer, and wizard, each overriding an attack method. But what happens when a knight picks up a magic wand? Or an archer uses a sword in close combat? With inheritance, this quickly becomes messy. You'd either need to create dozens of new subclasses for each weapon combination, or stuff your code with conditionals to handle special cases. The attack behavior is baked into the character type, making reuse and extension painful. This is where the strategy design pattern comes in. The strategy pattern is a behavioral design pattern that allows you to define a family of algorithms, put each into its own class, and make their objects interchangeable. Instead of hard-coding behaviors into subclasses, you delegate them to separate strategy objects. Let's break that down. At the core is a strategy interface. It defines the method that all concrete strategies must implement. These concrete strategies contain different variations of the algorithm, in our case, different attack behaviors. The context is a class that uses these strategies. It maintains a reference to a strategy object, but interacts with it only through the strategy interface. This means the context doesn't care what kind of attack it's using, it just calls the method. And the client? That's the part of your program that selects which strategy to use. It creates a strategy object, like melee attack or magic attack, and passes it to the context. The context has a setter, so the strategy can even be changed at runtime. This approach gives us flexibility. We no longer need to subclass character endlessly. Instead, we can change behavior by swapping out strategy objects. Let's look at a quick code example in C++. We define a strategy interface with an execute method: melee attack, ranged attack, and magic attack. Each implement this interface. The character class holds a reference to a strategy and uses it to attack. The client code reads input, creates the right strategy object based on the player's choice, and plugs it into the character. Swapping attack styles is now just a matter of assigning a different strategy. This decouples the character from the attack behavior, which is the essence of the strategy pattern. So, how do we actually implement this pattern? Here are the key steps. First, identify the part of your class that's likely to change. This will become the strategy. It might even be buried in a massive if-else block. Then, extract all those behaviors into their own classes, each implementing a shared interface. Next, modify your context class to hold a reference to the strategy interface. Add a setter so the strategy can be changed on the fly. Finally, in your client code, create the appropriate strategy object and assign it to the context. Now let's look at the pros and cons. On the plus side, you eliminate complex conditionals and gain the ability to switch behavior at runtime. You can add new strategies without modifying existing code, which follows the open-closed principle. However, it does introduce more classes into your codebase. And if strategies need to share state with the context, things can get complicated. Still, for scenarios where behavior needs to vary independently of the object using it, the strategy pattern is a clean